a somewhat encompassing theme here, I'm getting the nod at the back, sorry, is that everybody speaking now has got some past connection to this project, and took some training or took some time or took some fellowship time, worked with this group for a while, and then went and, I won't say did more interesting things, but applied the things that they learned in interesting ways to a broad spectrum of disciplines and research topics and applied domains. And so we'll see a series of perspectives of people who come through this grant. Maybe they'll make some small connections to what they did here, but I'll just quickly turn things over to people. To start off with, we have Jonathan here. Jonathan was both a grad student and a postdoc.
Correct.
With this program here at Harvard for a while. And then currently is a professor over at Northeastern, so made the intrepid voyage across the river, which, if you don't know Boston, it's harder than flying.
Pretty rough, yeah. Thank you very much, James. Thanks to everyone for coming. So what I want to talk about today is sort of not privacy per se, but rather a sort of an application of privacy. So a setting where the tools that are developed for privacy, both on this project and outside of this, can actually help with data analysis more broadly. And I'd like to acknowledge, so I've collaborated with many people on this work, including Kobe and Adam in this room. And also, much of this is really influenced by some very beautiful papers of Cynthia and her colleagues that laid out much of the intellectual framework. So let me describe the setting where I claim that privacy can help with data analysis. So, and let me start with sort of a cartoon picture of statistical analysis, which is that you begin by forming some hypothesis about the world, then you collect some data, and then you make some conclusion, and hopefully you consult with your friendly neighborhood statistician who tells you how to make this conclusion in such a way that the conclusion holds up on new data or somehow generalizes to the population at large. So this is great. This is the subject of a lot of beautiful work. But there seems to be some kind of consternation about whether this is really working out in practice. There are kind of increasingly provocatively titled articles with names like "Why Most Published Research Findings Are False," "Irreproducible Biology Costs, but at $28 billion per year." And this is even sort of leaving the ivory tower and starting to appear in like popular media. You can now even have a nationally televised show making fun of something called p-hacking. And so there are many causes for this non-reproducible research, or what I'm terming broadly false discovery. So p-hacking, which is a sort of derogatory term for the multiple comparisons problem, is one of them. But also kind of misapplication, misinterpretation of statistical methods, misaligned incentives, and even just out-and-out fraud or falsification of data. But that's not what I want to talk about today. I want to talk about a more specific cause of false discovery, which was kind of highlighted in a paper called The Statistical Crisis in Science by Andrew Gelman and Eric Loken. And I'm not sure if you can read this, but the little subheading says that false discovery is due to what they call data-dependent analysis, or what they call a garden of forking paths. And what that means at a high level is that often statistical practice looks more like this. It has some kind of cyclical feedback loop, where the conclusion you draw based on the data set actually is used to inform a new hypothesis, which is then evaluated on the same data. And while this is quite common, it actually invalidates most of the theory of statistical inference, statistical hypothesis testing. And this is what I call adaptive data analysis. So this kind of loop where the same data is reused for multiple purposes, and the purpose you use the data for is influenced by previous interactions with the same data, is what I'm calling adaptive data analysis. And it can come up in actually lots of different ways. So this is a very simple picture, but there's many different reasons you could want to do adaptive data analysis. So the first is when you just have some kind of specific statistical inference procedure in mind or statistical tool in mind that is naturally adaptive. So a common example that comes up all the time is you have some data set with some huge number of features. You want to select some interesting set of features and then fit a model on those features. And that leads to something called Friedman's paradox, which I'll actually describe a bit later. Or you may want to kind of do some sort of hyperparameter tuning. So often these feedback loops exist in statistical analysis. And in fact, in this textbook picture of how statistical analysis works, you'll notice there's a feedback loop drawn into it. So this is one way that adaptivity can arise, is through these kind of well-specified but still adaptive procedures. Another way it can arise, which is what was really highlighted by this article of Gelman and Loken, is essentially when this feedback loop involves like a real person, like this, it's like Salil's Harrier twin brother. So you can't read this, but this is an example where some researcher basically said, we did not find a statistically significant interaction, but we went back and we concluded that some of the variables we were looking at didn't really mean what they thought, so we took them out and then we found a statistically significant interaction. Now, I can't comment on whether those variables should or should not be included, but the point is that there's a feedback loop in this. They decided to change the study after seeing that they didn't like the results. Salil would never do this, of course. Okay, and the last, which is the most like unstructured, is when you actually just have some data set collected by, say, some agency or some research body, and that data set is just used over and over again by many different people. So not only are there kind of humans in each of these feedback loops, but there's like a big feedback loop among them. So how can we address this? There's many actual approaches for addressing this, and let me just give you like a very quick rundown of what they are. So the most common approach when you're dealing with false discovery and kind of statistical testing falls under the heading of hypothesis testing. And there are many flavors of hypothesis testing, but for the most part, they all make the strong assumption that the hypothesis you're testing was chosen independently of the data. And that's invalidated in adaptive settings. Another thing that's maybe more familiar if you've done, say, machine learning is to just split your data set into some kind of validation set or some holdout set. And this is kind of just punting the problem a little bit, because every time you want to validate on this fresh data, well, you have to throw that data out and get a new validation set. So the amount of data you need, grows rapidly with the number of times you want to validate. You could also try in some cases to just explicitly model what's going on. So instead of, if you're dealing with these well-specified algorithmic forms of adaptivity, you could just try to model them as a single algorithm and just roll up your sleeves and analyze it. This has been done. There's very nice work in statistics on doing this, but it really doesn't generalize to this unstructured case where there's humans in the loop, or where you just have very complex algorithms. Again, the last thing that's been proposed is to just kind of outlaw adaptive data analysis, require people to pre-specify everything they're interested in learning about the data before they get to see the data. That works pretty well if you're willing to submit to this workflow. So I claim that all of these approaches have some kind of undesirable traits. So in particular, we want something that's very flexible and can handle this unstructured adaptivity, possibly even ill-specified because there's humans in the loop. So what we'd like is some kind of general family of methods for preventing overfitting. It's another roughly synonym for false discovery, at least to me. So we want a couple of properties. We want that the methods are not tied to specific algorithms or problems, and in particular may not even require a specification of what the algorithm is. Okay, we want something that composes. So we want that as you go around this loop over and over again, we can kind of quantify how much overfitting might occur. And we want something that allows for kind of arbitrary post-processing, which is sort of another way of saying that we don't want to be tied to a particular way that people might use the data. We want something kind of general. And this maybe sounds too good to be true, but when thinking about this, I had sort of a flashback to the very first meeting of the Privacy Tools for Sharing Research Data project, in which Salil asked me to give a presentation. And so it was 2012, so I kind of trotted out like an overhead projector and slowly kind of fired it up. And I had a slide that said, what we'd really like is some method for protecting privacy that satisfies like exactly the same properties. And of course, I was talking about differential privacy, which does satisfy these properties. It was intended to solve a very similar problem of how do you give privacy guarantees that are not overly tied to one particular way of using the data. And so what we've been doing, basically, what this line of work is all about, is using differential privacy as a tool for preventing false discovery in these interactive settings. So kind of at a high level, the summary of what's been going on is there's been a lot of interest in exploring a new kind of flexible approach to adaptive data analysis. So one that seeks to give kind of general methods for protecting data from these sorts of false discoveries rather than kind of assuming or modeling them away. And this general approach was introduced largely in a paper by Dwork, Feldman, Hart, Patasi, Reingold, and Roth, or rather a series of papers. I also did some early work on this with Moritz Hart, and in some sense, a little bit of the idea actually goes back to Frank McSherry's work in 2008. And the key tool is to use differential privacy as a way of protecting data sets from overfitting, so a way of allowing people to analyze data sets adaptively without overfitting. And the key kind of conceptual message here, which I'll make like a little like example of at some point, is that while we normally think of privacy as a constraint, and of course, like in a formal sense, it is a constraint, there are settings where privacy actually gives the sort of best way we know of to analyze data sets adaptively with like strong guarantees that overfitting can't occur. So in some sense, adding privacy can increase the utility of the study you're doing. And another way of saying that is that in some settings, the methods that we currently think are the best possible methods we know of to prevent overfitting happen to also ensure privacy with some like reasonable parameter of epsilon. So I'll give you an example of that where some perfectly reasonable looking thing that seems to mitigate overfitting also just happens to give privacy. So I've done kind of a number of things in this space. I'm not actually going to talk about any specific paper. So I've done some work on kind of just improving the accuracy and generality of these methods. I've done some work on kind of new composition properties of differential privacy that are useful when you kind of specialize the tools of differential privacy to this new application. And I've also done a lot of work. This is sort of my like personal, I don't know, personal vice is proving that various things are hard. So I've done a lot of work on that, including one as of yet unwritten paper. I'm looking at Kobe to finish right now. So instead of actually talking about any of these works like in any sort of detail, what I want to do is just give like a very simple example of a setting where tools from privacy can help with interactive data analysis. And I'm not going to present like much math. I'm going to do it in a very like informal way. And it looks like there's going to be some notational issues from using a different laptop. So bear with me on that. So what I want to do is describe just a very simple binary classification task. And I want to kind of motivate it by machine learning competition. So things like Kaggle challenges, if you've ever heard of this, where you're basically given some data and challenged to come up with a good statistical model for say, solving binary classification. So I know this is a little hard to read. But basically what you're given is a training data set where each sample in the data is some set of information, some features, and then a binary label. And your goal is to come up with a classifier that maps these features to a label. And your goal, your score of the classifier is the fraction of labels it predicts correctly. So it would be easy to get 50%. You want to get as close to 100% as possible. Now, I, of course, don't know much about applied machine learning. So if someone gave me this task, what I might do is I might just try some random classifiers just to get a feel for what happens. So suppose I choose just random classifiers, which you can just think of as applying random labels to this training set. And I'm just going to look at the scores they get on my training data. And they won't be exactly 50%, just due to random chance. Some of them will do a little better than 50%, some a little worse. So maybe this one does a little worse, this one does a little better, that one does a little worse. But I guess I could take the best of these, and I could check whether this does better purely due to random chance or whether it's statistically significant. So I can do a classical hypothesis test. And given that I'm trying some large number of random classifiers k, I'm going to apply a Bonferroni correction, which, if you've never heard of it, is just a way of correcting for the fact that I tried a bunch of random classifiers. So one of them might be good, even if the typical one isn't. And I can plot like how well I do as a function of the number of classifiers I choose. So like on this axis, I'm choosing a larger and larger value of k. And this is the score. And this is 50%. And you can see that as I take more classifiers, the best one starts to do better. But this blue line I've plotted is the threshold at which I would get statistical significance, and I'm below it. So I will correctly realize that all I did was tried random classifiers. I haven't really done anything smart. But let's suppose I try to get a little more clever. So I say, I chose a bunch of random classifiers, but instead of taking the best one, maybe what I want to do is I want to actually try all of the classifiers that do better than random. So out of my k classifiers, about k over 2 of them should do better than random. And maybe each one of those is giving me some useful information. So maybe what I'm going to do is I'm going to select the ones that do better than random, like this one and this one. And I'll take some sort of majority vote of them. So it's not so important what that means. Really, all I'm saying is that there are methods for combining a lot of classifiers that do a little better than random into one classifier that hopefully does a lot better than random. And of course, now I still need to test for statistical significance. I need to check that I found something that does enough better than random that it's statistically significant. So here it looks like I'm doing a lot better. So if you look here, when I take about 30 classifiers, I actually start to do better than statistical significance. And when I take about 200 classifiers, I actually get 64% of the labels correctly, which at least to me sounds pretty good. Like I'm doing a lot better, certainly doing a lot better than the minimum threshold for statistical significance. So I'd never competed in this data science competition before, so I was very excited. So I called up Adam to brag about how well I was doing. Poorly chose pronoun. I called Cynthia to brag about how well I was doing. And Cynthia informed me that she had hilariously pranked me by setting me up to fail. She gave me a classification task with purely random data. There was no hope of getting better than 50%. The labels are just completely random. And lo and behold, when I submitted this and I tried it on new data, it turned out that, of course, I get about 50% of the labels random, labels correct. So I look very foolish. Cynthia really got me here. Well played, Cynthia. And so what happened is that even though I tested for statistical significance, I came up with this final classifier adaptively based on the scores of the first classifiers. So I had to look at which classifiers did better than random on my training data. And that's a function of the training data. That's a feedback loop involving the training data. And so the hypothesis test that we used no longer applies in this setting. And this leads to something called Friedman's paradox. And it invalidates classical hypothesis testing. And so this leads to kind of an idea for how one might try to prevent this overfitting. And this is where the connection to privacy starts to become a little bit more clear. So let's think about what went wrong here. So I computed some initial classifiers, and I computed their scores. And somehow, just based on the scores, I was able to find a new classifier that labeled 64% of the labels correctly. And if I had taken a large enough k, I would have eventually learned 100% of the labels. So the problem is that the scores of the initial classifiers are actually revealing a lot of information about the labels that I can use to come up with a new kind of obnoxiously chosen classifier. So the natural solution is to try to limit the information revealed about the labels. And the way that we're going to do that, unsurprisingly, is to use differential privacy, which is designed for exactly this purpose. It's designed to allow me to learn general trends that I can use to predict labels, but hide information about specific labels. So if this were a much longer, more technical talk, I would start giving you some theorems now. But instead, I just want to show you an example. So one of the most common ways to ensure privacy is to perturb what you report about the data set with some kind of noise, perhaps from a Gaussian. And so if instead of returning the exact scores, we return the score of each classifier perturbed with random noise, we can look at what value of the random noise gives me the least degree of overfitting. So here, I should conclude that I only get 50% of labels right. Anything better than that is just overfitting. And it turns out that the best choice of the magnitude of the noise is not 0. So there's some kind of interior optimum where if I add a little bit of noise, I actually do better. So here I add no noise. I get the most accurate estimate of the score on my training data, but can overfit badly. Here I add so much noise that I don't get anything useful. But in the middle, there's some sweet spot where I actually get the best overall accuracy. And that sweet spot actually gives me something like 0.4 differential privacy. So not only have I found a better algorithm for estimating these scores without overfitting, but I've actually ensured some privacy. And one can prove that this is a somewhat general phenomenon, although I'm not going to go into exactly to what extent. But basically, from this example, you can build a framework where you introduce some kind of algorithm A, the domo doll, that takes some data set drawn from some population and acts as an intermediary, injecting noise into what I report about the data set. So we allow some analyst that we don't understand and don't specify to ask us questions about this population. That's what we're interested in. And we want to design some estimator here that can give accurate answers and prevent the analyst from overfitting. And much of what this work shows is that in a wide variety of settings, the best algorithms we know of for achieving this are differentially private. So the best way we know to do this is often to perturb the data set with differential privacy. So that's basically all I wanted to say. I just wanted to give an example of how this connection works. I want to tie this a little bit into kind of the privacy tools project and what I think are some interesting directions that require some kind of interaction between people in different fields. So there's certainly many theoretical questions about this. But the one that's maybe most interesting for a broad audience is how to unify this with classical approaches. So we've kind of thrown out the baby with the bathwater a little. And then in practice, I think a very important question is how to identify kind of canonical use cases that we can use to study this. I think in privacy, having canonical use cases like the census applications has been extremely important. I think in this setting, because we inherently want sort of ill-specified data analysis, that's kind of the whole point, is to handle data analysis we don't understand. It's a little tricky to even get your head around what a canonical use case might be. So if anybody is interested in data analysis and thinks about this problem, I would love to talk. And I should just give a small plug. This is also the subject of an NSF grant I currently have with Marco. So we'd love to talk. And I just want to wrap up by saying that increasingly, there are more and more examples like this where privacy is becoming a useful tool for thinking about problems that on their face have nothing to do with privacy. There's a number of such examples. And so I'm sort of interested in thinking not so much about a privacy tools project, but like a privacy as a tool project. And so that's something that I would love to talk to people about and I'm very interested in. So thank you very much.
Okay, great. Are there any questions while we swap out slides? Any questions for John?
If there's no question, I'll make a plug.
Sure.
So this work has helped enormously in getting the statisticians that I work with to pay attention to more of the differential privacy literature. So I just wanted to encourage you to keep cranking this kind of work out.
I would love to. Thank you. It's great to hear.
Making another connection to John's talk. So one thing that was really nice in your example is that it example just revealed the value of epsilon for us. Unlike this problem that we have in privacy of this difficult choice of epsilon. Is there anything we can learn from this false discovery setting that can?
That's a great question. So I don't know. So as Salil's pointing out, here epsilon is just a tool. Like I only care about the epsilon that gets me the best accuracy. So I don't need to think. I don't need like the panel of census elders to determine epsilon. But
You might. Didn't you fix the target false discovery rate?
No, I mean, in this setting, I'm not exactly talking about false discovery rate. I was just talking about bias. So I just did a Monte Carlo simulation, and I just found the epsilon that empirically had the smallest bias. Now, of course, I controlled the game. Like I rigged the game, so I knew which one is actually the smallest bias. So in that setting, maybe you would need this.
I have a conjecture.
Perfect, thanks.
You specified your statistical objective and your privacy parameter, you'd still have a frontier.
But like if the statistical objective is like a one-dimensional thing,
So
like
normally we wouldn't use bias by itself. We combine it with the sampling variation, so we have mean squared error.
True. So maybe what John is saying is that I already have not managed to have epsilon be like self-revealing in the way you want, and therefore it's not helpful for this problem.
It's a conjecture.
So yeah, I mean, but there is some sense in which there's like demonstrably bad choices of epsilon in a way that maybe is harder to imagine, is not as clear for privacy.
It's easy to be inefficient.
Right. Like, but for privacy, it's not like obviously. I mean, except for like if your epsilon is so small, you get no utility. It's not clear like what is a. It's not clear like is 8.9 a demonstrably bad value of epsilon? Like I don't know. Whereas in this setting, like 8.9 might be like a demonstrably bad value of epsilon. I don't know. Anyway, my time is up. So.
Well, it's good sport of you to continue to take questions while we try to set up the next one.
Continue to like say things.
We will take a, hopefully a very, very brief.
I can start. Maybe, yeah. Even
Okay,
with,
then let me take your mic. Do you still have your mic?
No, I dropped the mic.
okay.
You're fine. You're fine.
Okay.
Oh, that looks like it might have been it.
Okay, let me introduce the next speaker is Michel.
Yes.
He was a researcher here at the Berkman Klein Center. And is presently a candidate for the bar in Geneva, and has written on, let's all stroke out, on regulatory policy and privacy regulation in Europe and in the EU rather, and looks like we're good to go.
Yeah.
Okay. Thank you.
Okay. Good. Thank you for the intro, and so good afternoon, everyone. So, as mentioned, I'm Michel Raymond, coming from University of Geneva, right now candidate at the bar exam at the law firm Bernstein Ball & Cairn. For going any further, I'd like to thank everyone in the Privacy Tools project for inviting me to give this talk this afternoon, particularly David O'Brien, Michael Mann-Cobin, and Alexandra. You're all awesome. I'm glad to be here this afternoon. I'd also like to extend my thanks to Gabriella and Kimia, who did all the hard work for getting me here. So much appreciated. My presentation today, as you've seen on the program, I wanted to make it into two parts, but I realized the first part was really important. So we'll have more of an emphasis on the question of privacy in the EU. And then at the end, I will have maybe a short rejoinder about some other takeaways that I took from the Privacy Tools project. So first, let's talk about my research. As you may have surmised, I come from the legal side of things. I came to Boston in order to study one specific area of law and of privacy law, and in particular the right to be forgotten, the right to be delisted, which is a rather thorny question when you come into EU law. Now, a few precisions about the right to be forgotten. The right to be forgotten is not actually one big thing in Europe. If you go into each country, you have different versions of what one could call the right to be forgotten. The term right to be forgotten rather describes one general idea, which means that you should not be held contemptible for facts that happened a long time ago. Let's say 10 years ago, I became bankrupt, and I don't want this information to be published anymore. Or I had a criminal conviction, or I had some embarrassing pictures taken of me when I was a teen. So all these sort of information can, in the EU, and depending on which legal concept, which underlying law you are using, can be targeted for deletion, for delisting in the EU. Now, I want to focus my talk on the issue that I was specifically working on, which is the right to be delisted. It's something a little bit different, but which was called the right to be forgotten, mostly in US literature. So the right to be delisted comes from a 2014 judgment from the European Court of Justice, in which you had one guy from Spain coming in and asking Google to have links taken down leading to a notice about him being broke 10 years ago, and he was put onto he was subject to auctions to recover social security debts. 10 years later, he did not want this information to be present on Google anymore. So he made a suit against Google, and under data protection law, he asked the European Court of Justice to have this data taken down. And then the Court of Justice said, yes, you have a right to take your personal information down from search engines. Now, let me make two things clear. The right to be delisted is not the right to erasure of data. It's about taking down links leading to content. I am not taking down a journal article. I am taking down the link from the search engine leading to that journal article. I am not even taking it down from Google. Google just does not display it when a search is made following my name. So it is not a right to erasure. Nothing gets erased from Google's server. It is only a right to prevent certain types of information from being published in certain contexts. So it's a rather narrow right. It is narrow in the sense of what is being deleted, but it is rather far-reaching in the terms of content that it can target. So not only all information about past convictions, but also embarrassing pictures, everything that happens in the past, and you want to forget, you can use the right to be delisted to take it down. Now, my research was on the geographical impact of the right to be delisted. The main question I had to tackle was, okay, if you have a search engine that is in the US and has no assets in Europe, is it being targeted by the right to be delisted? I was given a grant from the Swiss NSF to research this question. I spent 1 year at the Berkman Klein Center. And this ended up into a publication, which is a Berkman publication. You can have it free of charge from the internet. Now, my involvement with the Privacy Tools project, I was first at Berkman, and then I just joined the Privacy Tools project thanks from my involvement with David O'Brien. And I mostly worked with Kobe Nissim and the rest of the team on the privacy definition working group on bridging the gap between legal definitions and data privacy and computer science. I have worked on several presentations they have made, just giving my comments. My role there was just to serve as a sort of legal comment on the papers they were making, like as if I was the test subject for understanding the notion of differential privacy. Now, to be honest with you, my involvement with my project, my discovery of techniques such as differential privacy, it sort of challenged my pre-established notions of what was privacy as a legal concept. And this was the source of one of my major breakthroughs when it comes to the right to be forgotten and the right to be delisted. I remember that in fall 2015, in particular, I presented the right to be forgotten to Kobe during a presentation exactly in this building. And the presentation actually didn't work out. We spent a lot of time afterwards just debating what is the meaning of the harm when it comes the right to be forgotten. And I don't really think that I made my point clear, my point across to Kobe, what is exactly the right to be forgotten. So I felt like everyone I was talking to in the Privacy Tools project was actually quite mystified with the concept of the right to be forgotten. And this gave me food for thought. Was it me, or was it something else? After a lot of thinking, that's when I had my breakthrough. The problem was with the law and with the right to be forgotten. So now, I invite all of So now, I would like to invite you to think about the notion of privacy from a legal side. We've been talking about privacy since the beginning of this morning, and I would like to refer in particular to Ursa's talk about the meaning of privacy in law and how much it has evolved. Now, we've spoken much today about data privacy. About data privacy, which is how can data be stored and shared in a way that minimizes harm leakage of personal information and minimize risk of re-identification. Here, it is the data itself, the container, which is the main subject of inquiry. The main question is, what data can I share? How can I share it in order to protect privacy? And this is in this context that tools such as differential privacy have something to say. But is it really the same thing as the sort of analysis you're doing when you're talking about the right to be delisted or the right to be forgotten? And that's where I would say, no. Actually, it's also privacy, but a different kind of privacy. The right to be forgotten is about handling personal data. That is true. But here you have something else. You have the harm that this information has upon a person's reputation when communicated to the public. It's about what is the value of the information that is contained in the data when read by the public at large. And here you have different types of analysis coming into play from a legal perspective. So the questions I ask myself when thinking about the right to be forgotten are the following. Is the information relevant for public discourse? Is the person whose personal data should be taken off, is he a public person? Is it important to have that data out of the open? For example, if the person is a politician, then he would perhaps not have the right to be forgotten because it is of public interest to have that information out. So the right to be forgotten does not apply in the same way for every person and implies a pondering of values. And these values have to be found in each country's legislation. Each country's laws about freedom of speech and about social ordering. So you go into public interest defamation law, and here it's not about the container, the data, it's about the semantic meaning of data. And in this respect, some of the tools we've been talking about this morning are less important because you are trying to see should the data be taken down from a journalistic sort of perspective rather than a formalized data one. So it's a different thing. We both call them privacy, but they're not the same analysis. So in essence, both Kobe and I were speaking a different thing, a thing that was close enough, but still not the same. And this gave me the perspective to appreciate better where data law was going in Europe. So that's my breakthrough. So if you look at the article that gave birth to the right to be forgotten or delisted, which is Article 12b of the 1995 Data Protection Directive, it is actually a quite modest right to erasure. In 1995, we did not have Google, at least not in the form that we have today. When the directive, the Data Protection Directive, was enacted, they were not targeting these sort of situations with the right to erasure. The right to erasure was mostly for situations such as having an insurance company or a bank having data that is illegal because it's outdated, they don't need it anymore, or I have withdrawn consent, or another way, maybe they did not manage it correctly. Here it's pure data protection law. At the time, so this was the origin of this article, but it has nothing to do with the right to be forgotten. What happened afterwards is that the right to be forgotten, based on this article, on this concept of the right to be erased, sort of became deduced from that article from by the way of the European Court of Justice. So from a pure data privacy right, we came into a personal privacy right through a disposition, a legal disposition, that has nothing to do with these sort of inquiries in the first place. So this makes it rather difficult to exactly see where the right to be forgotten actually comes from. It is supposed to be data protection, but in all actuality, it is not. And this, in my opinion, encapsulates some of the trends we are seeing in terms of data protection in Europe. Urs has mentioned this, this morning, that privacy is evolving, is expanding. And I'm completely in agreement with what he's saying. It seems like everything is starting to be privacy right now. And if you look at the legislative trends in Europe, that's exactly the same. Urs has talked already this morning about the origins of data protection in Europe. And he's right. In the beginning, data protection was a very narrow kind of analysis. The first round of data protection laws were aimed at protecting people from government's use of personal data through automated means. It was only targeting these sort of situations, and we can also see that in the Privacy Act in the US. In Switzerland, for example, la loi sur la protection des données was originally made in this context and did not actually talk about protection of personality rights. It was placed in the context of personality rights, but it was meant to be a specific tool aiding against data leakage. So it was not supposed to be a general sort of protection of privacy. But with the European regime, starting with the 1995 EU Data Protection Directive, privacy started gaining a much amplified meaning that everything could be privacy. And this is exactly the same we'll be seeing in next year with the GDPR, which is set to enter into force on 25 May 2018, so a few months from here. It has a right to be forgotten, which is Article 17 of the GDPR. We still don't exactly know what sort of legal details that right to be forgotten has, because the legislature of the GDPR wrote that article before the main case of Google Spain from the ECJ. So we're sort of lost what this new right to be forgotten is or will be. What we know is that it will come with some problems because, as I mentioned, it sort of grows out of the whole privacy concept. And here I have a quote to share from Joris van Hoboken, who was mandated to give a report on these issues when drafting the GDPR. The problem with the right to be forgotten is that, well, actually, there's already a protection for the sort of thing the right to be forgotten is trying to aim at. There's already a set of laws in place that regulate the legality of making information about all others public. We have the laws of defamation, the laws of privacy, stricto sensu. We don't need data protection. But the thing is, since the EU legislature wants to put that under the umbrella of privacy, we have a wide scope of the definitions of privacy, then everything becomes part of the GDPR. And so we have a very different type of analysis coming into a formally data-oriented exercise, which does not make for much legal security, if you might agree with me. So the main takeaway I would have here is that first, I think we need to take a step back in the legal side of things and try to ask ourselves, what are we trying to protect? Are we trying to protect personal information? Are we trying to protect people's reputation? What exactly are we trying to achieve? And what are the tools we need for that? And I think the Privacy Tools project gave me the appropriate perspective on these issues, because it told me that, well, if you want to protect data, you have, for example, differential privacy, you have the data tags projects, et cetera, et cetera. And if you want to protect other kinds of privacy, such as personal privacy, dealing with the right to be forgotten, then maybe you have to find appropriate legal tools to solve these questions. So this is the main takeaway I took from the Privacy Tools project, but it's clearly not the only one, and there I go to the second part of my presentation. First thing, I think there is an enhanced need for us in the legal profession to talk with computer scientists and engage with them and bridge the gap. We've seen through today that this need is even more salient today. And I'm thinking not only in terms of smart contracts, as I said, as I mentioned in the slide, but also so yeah, smart yeah. Yeah. Sorry, I just had the other thing I had is that the second thing that I took from the Privacy Tools project is that you need to have clear models to present to stakeholders when you want to talk about privacy, and if you want to present working solutions to their own questions. So this is a personal experience that I had as a consultant, as a legal consultant. I worked with the EPFL, so the École Polytechnique Fédérale de Lausanne, working with some of their issues they had about privacy, and they were not really interested in having a lawyer tell them exactly what to say. What they were interested was actual solutions to the question they had. So I showed them a demo of the data tags project, and they were completely enthusiastic about it. And since they had a working way of seeing what was the data tag system and allowing them to proceed with the demo themselves, I think it made the message go very clearly. And so developing working models in this sense makes it easier for stakeholders who are not lawyers, who are not computer scientists, who are just sometimes administrators, can be a very efficient way of communicating privacy. And so with that, I am done, and I thank you for your time and for your patience. Thank you.
Here's a set of slides. Any questions for Michelle?
Yes, yes.
So you made this point about needing the right toolbox for what you're trying to protect. At this point in time, do you think that the right to be, the delisting is the right tool, or do you have ideas of what other tools might be to achieve the what is trying to be protected by the right to be forgotten?
Well, the interesting thing is that even in Europe, we don't really know what exactly we are trying to protect. As I mentioned earlier, the right to be forgotten has very different implications from country to country, meaning that in some countries you have certain things that are protected, and in other countries you have something that are not protected. And even in the context of European right to be delisted, you still need to find a way to know which law applies and then derive a model about that. So I think the first step that we should have is to try to define exactly what are the standards. Because if we don't know what are the standards, we actually don't know what we are trying to protect. The right to be forgotten for me is more of a stopgap. It was more of a politically informed decision made against Google itself. More of the idea of saying, okay, we know we love privacy in Europe, in the US, you love privacy a bit less, we should do something. But it was not a very thought out move, which did not give much way for stability of the law and for informed decisions on the right to be forgotten. So right now we have a system that is mostly alimented by Google itself, but not actually by any other stakeholder. What is the way out? I think we should rather be talking from jurisdiction to jurisdiction, multiple stakeholders talking with each other and actually trying to sort out what sort of problems we are trying to look at and how to solve them.
And this project, as it's been described, between many different disciplines, in particular social science and the quantitative social science and applied statistics and computer science. And Vito came here as a postdoc with a PhD in quantitative political science and worked as a postdoc at the Institute for Quantitative Social Science when I was there. And now is a professor of political science at the University of Texas at Dallas. And sorry, I get that one wrong all the time.
You got it right.
Right. And he will talk. He works now on machine learning models in the social sciences and on quantitative models of political conflict and software tools for quantitative social scientists. And we'll talk about that career trajectory coming out of this project. Thanks.
Great. Thanks, James. So James didn't mention anything about privacy. But when I came to IQSS in 2013, I actually didn't know anything about privacy. At UT Dallas, I actually now offer a class there called Data and Policy, which was informed by many of the many things I learned while working with the Privacy Tools Project and at IQSS. So that was a great opportunity that was afforded to me through the Privacy Tools Project. But as I mentioned, when I came to IQSS, I actually came to work on Zelig, which is an R library for estimating statistical models, and also to build a tool for using Zelig from Dataverse. So this combination of Zelig, Dataverse, and the Privacy Tools Project really spurred a lot of the initial development on Two Ravens. And that's what I'm going to talk about today, is the Two Ravens project. James is a co-author on this project as well. James was a senior research scientist at IQSS while I was there. After leaving IQSS in 2015, Two Ravens received some minor funding from UTD to kind of keep things going. Some other funding through the Modernizing Political Event Data grant through UT Dallas, which I was actually asked to be on because of my involvement with, or my work on Two Ravens. But more recently, we've received funding through a DARPA grant, and it's just been in the past 6 months working on the D3M project that we've really been able to realize a lot of what we had envisioned with Two Ravens. So, for example, we've been able to build our team. So that's let me see which is the pointer here. Okay, so that's me and James. We've been able to hire Raman Prasad, who's back over there, as a full-time developer. Aaron Lebo, Sruti Jain, and Kripanshu Bhargava are all part-time graduate students at UT Dallas who work with us on this project. So what is Two Ravens? In the simplest sense, Two Ravens is a tool for statistical analysis. Right, so you could do things like explore data, look at bivariate relationships, scatter plots, different distributions, and summary statistics. You can also annotate data. Okay, so you could do anything from simple descriptions of a particular variable to specifying the unit of analysis for a data set and keeping that specification in the metadata, okay, so that it's tied to the data for future use, as well as things like semantic role labeling and stuff like that. Using Two Ravens, you can construct and estimate statistical models, and not just using Zelig, but other R libraries, and now with D3M, various other problem-solving systems. And you can compare and curate empirical results. Right? So you could build up certain models that are estimated on a particular data set over time and compare them to one another. So that's sort of the tool, but that's not really necessarily what the project of Two Ravens is about. Right? The the project, our goals on the project are larger than that. Okay. One goal is to connect people with data. And I realize that's a lot of the Privacy Tools project, that's a lot of Dataverse, but that's also part of Two Ravens, is connecting people with data. And in this sense, it's a tool for education as much as it is a tool for research. But there is a research component as well, a large research component as well, and that involves accumulating knowledge and learning from users and learning patterns about how people interact with particular types of data. Right? And the idea is that we want to use the knowledge and the discovery of these patterns to improve the quality of results in the literature and so disseminate this knowledge. Much of our ability to do these things, right, to connect people with data, to accumulate knowledge, and to use that knowledge to improve the quality of results, much of that comes from the design of this project. The design of this project was also heavily influenced by Psi, and at least in the planning of Psi. So I'm just going to walk through a little bit of this here. And this is a basic architecture diagram that I drew up. It's probably an extreme simplification of what's going on. But every data set has an associated metadata file with it. Right? And our user interface is launched from that metadata file. It doesn't actually use the data itself to launch. That metadata file is populated using our pre-processing script that we wrote for the Two Ravens project, as well as any auxiliary metadata, such as the DDI file, for example, that comes from Dataverse. And we'd use that to specify things like the data citation, for example, as well as other inputs from the user. That stuff gets stored in our database. Right? Also stored in our database are workspace information, so that users can save and restore their workspace. Any manipulations that a user might do on a given data set, right, so that in the future, if you're sharing a workspace, you can ensure that future researchers will be working on the same exact data that you are. And importantly, any results, right, that one might accumulate. And these results aren't possible. We can't retrieve these results, or at least most of them, from the metadata itself. Right? So what we have are these server applications that anytime a user wants to actually perform some computation on the data itself, okay, all the computations are done server side. Right? So it basically just sends off a request to the server and says, hey, do this operation on the data set. Okay, so the user's never actually touching the data. This is also where, for example, the privacy functions would live. They would sit in this set of server-side applications, as well as any DARPA D3M solutions or exploratory, any types of exploratory data analysis. Okay. So that's sort of the overarching sort of architecture. It's also important to know, and probably fun to know, the most fun part of our project are these little pebbles. And the fun part's going to play a role a little bit later as well. But we specify the models, statistical models, using the language of directed graphs. Right? So here we're just saying that horsepower and weight are predicting class. And in this instance, which is a new grammar that we've recently added, we're saying this set of variables and any transformation of this set of variables or function that you want to perform on any one or more of these sets of variables can be used to predict class. It's a little more of a sort of machine learning. You use these variables, sort of mine some type of result for predicting class. And with that, I'm going to show a quick demo. Actually, before I do that, we have an instance of Two Ravens. So Two Ravens integrates with Dataverse, and you can go on Dataverse, and if you ever see that little Explore button next to a tabular data file, you can launch Two Ravens on any tabular data file on Dataverse. we have a link here where you can go and use 2 ravens from our actually this is linked to from our website as well, on this particular data set. I'm just going to show a brief demo, though, to give you a sense of the tool in action. It's only about 2 minutes. I may have to stop it from time to time. We're not going to show every feature here, but just some of the primary ones. So this is our D3M application. Okay, so this isn't necessarily the tool that you'll see through if you were to launch 2 ravens on Dataverse, but rather the tool that you would see in the D3M application. And we envision, future applications of Dataverse being developed as well. So you see here, right, you have all the variables in a particular data set listed in the left panel. I didn't start it yet, so the modeling space is currently empty. You'll see it populate real quick. So let me actually just start it. Okay, so you'll see the variables here in the left panel. You'll see this is the class. This is our dependent variable, or the thing that we're trying to predict. And here are the set of all the other things that are predicting class. Okay, so let's say we didn't want particular features to be part of that sort of unrestricted group space. Okay, we want to use them to estimate perhaps just a single relationship between that variable and the dependent variable. So we're going to remove them from the group, and then we're just going to draw connections to the dependent variable in particular. Let me just stop that real quick. If you notice, origin was clicked and it was changed color. So when you mouse over, you get these certain tags that are available. And those tags allow you to contribute some of your user-specific knowledge about a variable to help solve this problem. Right? Happened kind of quick, but origin, we tagged origin as a nominal variable. If you see, there are only 3 categories. This is origin of country. Okay, so it makes sense to tag it as a nominal variable. You could see various subsets of the variables and also select particular subsets that you might wish to estimate this model on. You do that by brushing, so you select the bar plot or brush over a distribution, and then you can click select or just go ahead and estimate this particular model. So this is the D3M project, so there's all these other sorts of additional problem specifications that we have to work out. So those are shown quickly, and then we click estimate. Right? It packages that information up, sends it to our server application, which then estimates the model and sends back the results. All right? So that's what we're seeing here. This is our first model. This is our set of results, as well as some plots that were constructed. Other things we can do, and this is enabled by a nice feature in Zelly, is we can see how particular quantities of interest change as we set different values of x. All right, so here we just set those 2 different values of x, and you can see how this quantities of interest, so particular predicted values, distributions of predicted values will look differently. And here we're just going to see that again. And as we're doing this, you'll notice that models are accumulated here, and they're stored in our database. So this would be one particular workspace, right? And that workspace is shareable for others to then come and view those results. Build up a history here. And now what we're just going to do is just switch over from a regression problem to a classification problem. All right, so we're going to take that same origin variable, which again is nominal. We're going to specify that as the dependent variable. And we're going to select the classification. Rather than regression here, we're going to tell, hey, this is a classification problem. So send this model off to the D3M algorithms that are being developed and sort of crank on this classification problem. All right, so you could think of D3M as, in some sense, we saw Kaggle mentioned. In some sense, D3M is just like automating Kaggle in a way. Right? So they're developing these kind of back-end algorithms, and we're specifying a problem and sending it to them and saying, hey, go ahead and crank on this problem. And again, that model will also be accumulated here. Right? So you can then toggle through these things and compare the results. let me flip back to, okay. Okay, so in a number of ways, the architecture and the design really helps us to make some progress on these goals, in large part by what's stored in the database. We'll talk about that in a minute. So some of the most recent progress that we've made on this project, as I said, has been since we got this D3M grant, and it's really, even more than that, been in the last 6 months. And so we've been able to actually, we've been able to put in place this Django web framework that allows us to route requests. So if it's a particular unrestricted problem that we're going to send off to D3M problem solvers, or the more restricted problem that we might see, like a user specify when they're using it on Dataverse. We've been able to write much of the front end in Mithril, right? So it's a front end framework for rendering various types of various ways that the interface might be designed, depending on depending on which version of 2 Ravens we're using. We've put the database in place to save and restore workspaces, as well as to store results. We've implemented a new explore mode, all right, so focus less on actually estimating statistical models and more on descriptive data analysis and various API documentation. So in the future, where we're headed with this is, well, we're going to continue developing the things that I've suggested. We also see a greater role for this project in education, and not necessarily, so there's obviously a research component and a meta-analysis component that might be of interest to many people in this room and many other people conducting academic research. There's also an education component for undergrads and even students at community college and high school students as well, that is enabled by 2 Ravens for precisely some of the reasons that we see in our design. All right? So the fact that workspaces are shareable, so that there's a single data file for the instructor and the student. In other words, the students can't corrupt the data. And if I teach applied regression, and this is one of the major problems we have, the students change the data. And then they wonder why the results don't work and why they don't look the same and all that. Well, it's because they changed the data. You could link directly to it from the syllabus. Right? It's a link, just a single link directly to the workspace on your syllabus. You put it there one time, and you don't have to worry about it. It only requires an internet connection. So the tool runs completely in your browser. Right? So there's no need for a computer lab on campus. So this is one of the reasons we think it's going to be very valuable for high schools and community colleges to sort of do this type of instruction with data and bring it right into the classroom, because you don't need these labs. Right? You can do it right there. All you need is a connection to the internet. And the software is free and easy to use. And the pebbles. Right? Pebbles are fun. So pebbles are fun, that encourages people to use it more. And they're more fun the younger you are. Okay, so another one of our goals that we're pushing towards is for replication, to use this as a tool to improve replication. Right, so it's really a pretty simple idea, which is to have 2 Ravens have a readable replication file. So right now on Dataverse, you get the data and you get like your R script that you use to replicate it. Well, if we could just like load that up, right, read it through 2 Ravens and harvest those results and store them in a workspace for a particular data set, we can then use those results in all sorts of ways. Right? We can use them for all sorts of metadata analysis. We could use them to track, for example, the trajectory of a research problem over time. See what new theories are being developed, so that future researchers don't have to recreate the wheel, so to speak. We could also do what I like to think of as sensitivity analysis on a scale that would satisfy Edward Lemur, which means we can see if particular findings hold up across large numbers of data sets and across all different types of specifications. If we can manage to get these type of results in a database and in a way that is easily accessible and understandable. Yeah. And I'll just conclude with a couple lessons we learned, since we're also talking about the things we've learned since working on this project. And for me, maybe less relevant to some of you in computer science, but to me, on an interdisciplinary project, so the language is tough and language is a barrier, but I think actually incentives are harder, right? We can learn the same language pretty quick, but it's the incentive structure that's really different. So all my graduate students are in political science, right? They're not aspiring developers. And actually imagine, even in computer science, most of your PhD students are probably not aspiring developers, they're researchers. So you can't really expect them to enthusiastically jump into software development. Like, they might be forced to do it, and they might do it, but you can't really expect them because the incentives aren't really there, right? The incentives that are published and to get a job, not to necessarily develop software. But there are large numbers of students on campus who are aspiring developers. Right? Many undergraduates will jump at the opportunity to work on a research project and just write code for that project. And they're more than happy to do so. And so anyway, that was a little piece of information. That was something that I picked up along the way. I thought maybe might be helpful. The other thing that I've learned is how useful design documents really are. And I never understood how useful a design document was until we were able to hire Raman, and he puts forth design documents pretty much continuously. It's almost like a means of communication to James and I, and more to me, since I'm not physically present. But they're incredibly useful. And as faculty, we don't do these things on a regular basis because many of us don't design software on a regular basis. And so having these design documents, we don't know how to do this, and our students often don't know how to do this. And so that's actually where I see probably the greatest need for professional developers or various types of institutional assistance is in developing these design documents at the proposal phase, so that you pretty much know what you're getting yourself into. All right. Thank you.
While we're putting in slides, swatching sheets.
Yeah, go ahead.
Any questions?
Yeah.
I wanted to acknowledge that we have at least one person in the audience who knows who Ed Lieber is.
All right, fantastic. I was a little concerned about that. This is the clicker.
Who is Ed Lieber?
He's an economist. Take the con out of econometrics is his other books. What?
Yeah, sure.
You're all done.
I'm done, yeah.
Business school, he's business school.
Okay, great. And
Thank you. Is your mic switched? Make sure. Yeah, it is. Okay, good.
okay. Next we have Adam. Adam was a writer in residence and a fellow with LaTanya Sweeney's data privacy group here for many years, just down the hall. Adam wrote an arm length of articles and works on data privacy that would put anybody who thinks that they're productive to shame. And then also 2 books on data privacy during his period here. And we'll synthesize all of this somehow into a talk right now.
Thank you very much. So my work is about the human face of personal data, the commercialization of our data and what it means. And so I get to have the great fun of going out and talking to the people that collect the data and the people who are impacted by this. So it's the human story. This book here came out earlier this year about the medical use of our data. The first book I wrote while I was here is What Stays in Vegas. And initially I thought I'll write a book about the world of our commercial data, what happens to it, and I'll have a chapter on medical data. This turned out to be so complicated to explain what happens to our medical data and to make it interesting with human narrative stories that I had to put that aside, write an entirely separate book, and that's the thing that came out earlier this year. In essence, I had a very simple question to begin with, and this is something that Latanya Sweeney in the Data Privacy Lab came up with, is what happens with our data? So we think as patients who go to the doctor's office, you're speaking to the doctor, the door is closed, nobody else hears that conversation. This is an intimate medical problem that I'm describing to you, my doctor. However, as Latanya has outlined, there is a vast swirl of information that goes with you and your medical problems. Some of it is related to your medical care. Much of it is not. Much of this circulation of your medical information is a commercial trade, and it is about selling and promoting the sale of drugs and other things. So I thought, let me take this chart as an example and figure out, well, what's going on here? Who are the humans that are gathering the data? How did this business evolve? What is going on? So in the simplest, you think of that relationship with the doctor, that closed door, nobody else knows what's going on. You'll see in this photo, however, there is a computer. And the computer introduction into the doctor's office means that data is easily gathered. And in recent years and in recent decades, the people who do the computer systems for the doctor's offices have begun to sell data. So you visit the doctor, he or she writes down the information. That information is often sold for commercial purposes by the software companies. That's only one of many points in which your data is then a commercial product. The visit is paid for by insurance. Now, the insurers are often selling the data as well. Until now, Aetna was a rare exception amongst companies that did not sell data. Aetna is talking about merging with CVS. CVS is a company that does sell your data. They are one of many in the pharmacy business that sell your data. Traditionally, you are worth 1 penny. So what drugs you take are worth 1 penny per time. Now, that information from the doctor's electronic record system, from the insurance system, from the pharmacy system are all collected on an anonymized basis and create a dossier about you and about hundreds of other millions of patients that is incredibly detailed, again, overwhelmingly for commercial purposes. The doctor sends you to get an injection or to get a blood test or to get a urine test or a sample of your tissue. That information is also sold commercially. Now, this comes from inside of you. You may think this is very intimate. Surely this stuff is not for sale. Well, it is, and it is increasingly a big multi-billion-dollar business, not only in this country, but internationally. Now, this is an example of a company that sells. So if you go to Quest Labs, which they operate here on campus, as well as many other places in the United States, they do sell your blood test information. And so all of this presents what I call the paradox of patient data. You don't have access to the information about yourself when you need it most that's comprehensive, all of your medical records so that your medical healthcare providers can give you the best possible care. But on the other side of the equation, there are data mining companies that operate and have dossiers about you and hundreds of other millions of people in this country for this business. This business is overwhelmingly about selling drugs to doctors. They are the gateway to get to these audiences because they are the ones who prescribe it. Your information is sold in two ways: anonymized data, identified data, and sometimes both are put together in interesting data algorithms so that you can target advertising and sales to likely people suffering from certain ailments. So first, anonymized data, as we talked about before, no patient name, but it has the age, gender, partial zip code, and doctor's name. Now, this doctor's name part is significant because you may know that Dr. Jones is typically prescribing drug A. I work for drug company B. Dr. Jones, I'm coming to visit you. I'm bringing you some cakes or some gifts. I'd like to take you out to lunch. Let me tell you how great number B is, my drug company is over the other one that I know from my internal dossier of your patients what you're prescribing. The blood test that I told you about, you've gone to have a blood test on Thursday. I, the commercial company selling drugs, see that you, Dr. Jones, have a patient that is now suffering from a certain ailment. I'm going to go see you on Friday. Dr. Jones, you have a patient with this terrible disease. Let me tell you about the great new solution that I have. Now, the patient has not yet got to see Dr. Jones. The patient's coming in on Monday or Tuesday. Dr. Jones has already received a sales call based on this anonymized medical information that's in circulation. This is what this data, this medical data, is overwhelmingly collected for and overwhelmingly used for. These are some of the companies that collect and use the data. Some of these names will be known to you, and some of them may not be so familiar. IBM, Optum, HealthCore, Blue Cross Blue Shield has BMI Health. These are some of the labs that collect in the electronic medical record system, Cerner, LabCorp, Quest Diagnostics. And sometimes you might not know the names, such as Practice Fusion, which provides free service for doctors, a free electronic medical record system. But these are companies that sell your data. You have no say in this matter. This is allowed under the rules of medical data transfers in the United States, the HIPAA rules. Now, I thought, well, there's got to be an interesting story behind this. How did this all develop? Who are the companies doing this? This company here, IMS Health, is the company that for more than 60 years has led the way. This is the big giant of trade in these dossiers on patients. Now, interestingly, I wrote in a book a lot of information about IMS Health. It had been under the radar for many, many years, and my book is published earlier this year. Just about a month ago, IMS Health, for the first time subject to public exposure, changes its name. They changed their name to, it's a little off on the slide, but IQVIA, which looks like IQVIA, but they want you to pronounce it IQVIA. So they have rebranded themselves when we have now focused a little bit of attention on them. Now, this is the kind of information they gather: medical claims, mobile data, non-retail outlet data, EHR data from hospitals, provider software, genome registries, patient registries, provider claims, government health plan, and pharmacy claims, all mixed up. They're all matching all these different things together by matching numbers so that there is this extensive dossier on individual patients with thousands of data points. And of course, this is very interesting for sales, for marketing. And as I mentioned, this company and the others that trade in our data are quite secretive about it. They shroud the operations in secrecy. They do not welcome this examination. And as I said, when there is an examination, curiously, the names change. It is harder to follow the trail of what is going on. So the father of all of this might be this man called Bill Froelich. This is from the IMS webpage. 1954, this man's name is mentioned once. It says, Bill Froelich, an advertising executive, and David Dubois, a visionary, formed IMS, a market research company that enables organizations to make informed strategic decisions about the marketplace. Now, his importance is equal to Ray Kroc is for hamburgers and McDonald's, or Henry Ford is to cars or whatever for the medical data mining business. This is the guy that starts it all. He is mentioned once on his company website. I thought there has to be more to this guy's story. It's got to be interesting. So here is who this man is. He is born Ludwig Wolfgang Froelich in Germany, and he comes to the United States. He has a little transformation of name, becomes L.W. Froelich or Bill Froelich. He sets up a medical advertising agency in New York City after World War II. There's a big explosion in drugs, and medical advertising is doing very well. So he sets up one of the two big medical advertising agencies. Think of Mad Men. This is the era in which he is operating. This is his big rival, Arthur Sackler. And Arthur Sackler sets up the other big medical advertising agency in New York City. These are the two big players that would, in the world of Mad Men, be competing fiercely against each other. This Sackler name may be familiar to you because he was a big donor. So if you go to the museum 2 blocks away You will see the Sackler part of the Harvard Art Gallery. You will see this temple in the Metropolitan Museum, the Sackler wing where the Dendor Temple of Egypt is located. Froelich decides to set up this other company, which is IMS Health, and it helps provide information about what drugs are selling where in different parts of the world. And so it helps to convince people to advertise more. You have 30% of the market in Germany. You need to advertise more to keep ahead your share of the market. You have 30%. You need to advertise more because you're behind in second place. So IMS Health, as a company for marketing, starts up in this way. It helps the advertising business. Now, in 1971, Froelich dies. This is his New York Times obituary. This obituary is filled with errors and falsehoods. And it is because Froelich himself, a very dapper guy who took people out to the opera, who was a sophisticated European and impressed clients greatly, was extremely private. And it is in the very DNA of this company and some of its rivals that they want to be extremely saying little about us, even though they have extensive amount of information about us. One of the questions that intrigued me is, why did Froelich come to the United States in the 1930s? What was his deal? And I went back and found the people who knew him now in their 80s and 90s to try to put together the story. The question, was he a Nazi? Was he a Jew? There was, what was the circumstances? I found this from the FBI files, an FBI note from 1943, wondering, was Froelich a Nazi? He had relatives in Germany and was a member of the German Arbeitsdienst, a working camp in Germany. But his closest relatives said, no, he wasn't. But they said, no, he wasn't a Jew. Our family is not Jewish. However, I went back into the archives. This is Froelich's 1934 application for university to the University of Frankfurt. Believe it or not, I was able to obtain this document. His application to get into university reads as follows. Although I am not an Aryan, I am applying for admission to the university. My father was a veteran of World War I, and my mother worked in a munitions factory. So Froelich was a Jew who came to the United States. He was also a gay Jew. He had good reasons to leave Nazi Germany, and throughout his life, he hid these facts. He hid his heritage, and he hid his sexual orientation. Again, this guy setting up this business. But Froelich's biggest secret was only revealed in 1971 after he dies. His company goes public. They sell it onto the stock market. And in the fine print of the offering to the public is the following sentence. Most of the proceeds of the sale will go to the following people: Mortimer Sackler and his brother Raymond Sackler. Now, you're thinking, wait a minute, he just said that Sackler was the main rival to Froelich. They had the two rival agencies. Well, Sackler and Froelich were in cahoots on Madison Avenue, what they called Madison Avenue. They were sharing clients for advertising, and they formed this company together, with Sackler being the secret partner. Arthur Sackler was the big dominant brother during these early years. He gives it to his two lesser-known brothers after the death. His share of the company, this is worth $6 million or so. Now, these two names may be also familiar to you from recent articles. They have gotten a lot of attention in the last 2 or 3 months. Here is one of those articles: the family that built an empire of pain. Because the Sackler brothers that I just mentioned have this company that has made a lot of money off of the opioid crisis. And that was, the first one was in the New Yorker. Here's another one from Esquire magazine: the secret of family making billions from the opioid crisis. So just as secretive Sackler was in the realm of medical data, they have been in this realm of selling data, the other two brothers. And just last week in the New York Times, this article: should people and institutions taking this charitable money be concerned about the two brothers and their background in making so much money off of opioids? So when you look into the background of these people, it is quite interesting. In the 1970s, after the death of Froelich, is when the world of personal medical data sales becomes more common. This is when the digitization of medical records and pharmacy records becomes possible, and the big sale to commercial entities starts taking place. So the people who I talked to, who talked about gathering this data on doctors and profiles openly today in their retirement, say, yes, it was a very secretive process, as this man here said. We weren't going around telling anybody. We had nothing to gain by letting them know. The drug companies did not want their reps telling the doctors they were watching. That's a bad scenario that when happens. So the salespeople from the drug companies went there, had all this information based on this personal medical data that they had, that doctors didn't know, that patients didn't know. Often to this day, the nurse applying the needle into your arm does not know. The doctor himself may not know about all of this vast data gathering. What's the problem? Well, as you've already talked about, re-identification is easy. The one place where I have found where someone obtained a data set of this anonymized patient medical information was in Korea. This man is a brain scientist. He became a television reporter. Someone from a company that was selling data to IMS in Korea comes to him and says, I am perturbed by the sale of this medical data. Can you do something about it? He broadcasts this in Korea. A criminal case starts, a lawsuit starts, and there is a data set that results, which I am able to obtain, and I give it to Latanya and the people at IQSS, and they are able to publish this paper, which finds that the solution, the great encryption that this company is using is A is 1, B is 2, and the only twist is if it's an odd or even number. That's the genius scheme that they used. There's also identified data that's in wide circulation with name, address, phone number, about your medical details. So I would go to these big conferences, and here's one thing that I discovered. I would go to the conferences where data brokers are selling information. This is a list of baby boomers with erectile dysfunction, 1.7 million American men at $85 a piece. So I go up to them and I'm like, hey, this list, this is really interesting. Tell me about it. And they say, these men have volunteered this information to us. And I'm thinking, 1.7 million American men, I don't even think one guy is going to give you this information. So I say to them, listen, let me buy 1,000 names. There's the price, $85. I will buy 1,000 names. And they ask me, well, what are you going to do with this information? I'm going to write them, I say, and I will say, men, did you know, A, that you were on this list, and B, did you receive any useful advertising related to your reported condition? And they said to me, that would be an immoral use of our data. And that's the problem. These companies are very secretive. They tell us very little about themselves, but they know a great deal about us. You can buy whatever medical condition lists you want, named, address, phone number, so on, people with cancer by state, bladder control problems, STD meter of mature singles that may have a sexually transmitted disease. So the problem with all of this vast trade in our data is not that it exists so much, but that ultimately when this becomes more widely known, people could lose confidence in the system, because you have to have the confidence to tell your doctor, your nurse, your care provider, here is my condition, here is the background, please help me as much as you can. Now, there's lots of things about which data could be gathered that would be interesting for social scientists. So take confessions to your priest or to your religious figure. That would be really interesting to know what people actually say when they confess. But if you were to add a broadcast mechanism into this and share that data even on an anonymous basis, that would change that relationship. So likewise, when you take the operation, you take the room of the doctor and you interject this vast sharing of data unrelated to the care of the patient, you could have a trust issue that evolves out of this. So this is what is so interesting to me about all of this. I wanted to, in my last minute, pay tribute and thanks to all of you here who have supported me in my work, and especially to Latanya Sweeney, who has inspired me in this and pressed me forward to figure out how all of this works. And as I say, this is an attempt to bring to life, to animate all of the amazing work that you do in the field of data science, because this is about real people, and it could have very significant repercussions if this system is not built properly, and often is built by the commercial world without really asking the public what they want to do. I would like to encourage a public discussion of what balance do we want to have when it comes to sharing our medical data. These are my books. These are my contacts. Thank you very much for listening.
Were you able to interview any current or former employees of IMS Health or similar companies?
So I have interviewed several hundred people related to this book. So it's about original research, including the Sackler brother who died just this past summer at age 92. How did you get this $6 million? For example, it's like, oh, it just fell in my lap. I had barely nothing to do with that company. There were many former employees that were glad to talk to me, but the companies themselves do not want to detail what they're going on. So the companies were very reluctant to speak. Today, the former workers were very happy so that I could build together this picture. But I'm someone who has worked 5 years in the Kremlin, covering as a journalist what's going on behind the walls in Moscow. I had to use those same investigative skills to figure out what's happening to our data today. Anyway, it is break time. Thank you very much.
Are there any other questions?
Oh, okay.
A couple of small questions. Just first of all, I'm wondering what the connection is between the personality of the founder and, like, you know, the data broker industry. Why you think there is? I mean, I see he was a secretive person, but is that it, or is there something else? And just a small correction, IMS didn't rebrand. To the best of my knowledge, they were taken over by Quintiles and merged into it, and thereby came this new.
So Quintiles and IMS did merge in the past year, and then they renamed themselves. That is correct. So the first question, which is one more time, the first question is on
The personality of the founder.
Well, I mean, because this great paradox, I feel that these companies that have, the IMS boasts that they have more than 500 million dossiers on individual patients worldwide. Yet we, the public, know very little about this company, the renamed IQVIA. And there's Symphony Health, there's others. We know very little about them. So I said, let me turn the lens onto them and see who are these people that are gathering our data. And it turns out that many of them are extremely secretive. And so Froelich was one, the founder of this company, this $20 billion plus company today, was one who had many secrets, and secrets that would be exposed in the media in a much more different way in today's world. It just seems to me that this is the DNA in which this company and some of the others have emerged. And it's only fair that if they know so much about us, that we could know a little about them.
Any other questions? Let me thank all the speakers in this session, and we have a coffee break until the hour, I believe. And we'll be back, and we're doing very well for keeping on time. And thanks everybody for our speakers and all the travel. I believe we racked up a cumulative 7,000 to 8,000 miles between our speakers. So thank them all together.
All right, hello everyone. It's the final session of the day. We are going to be hearing about some of the directions that we're headed in going forward. Of course, the border between work that we've done and are doing and the future is not a precise one. So you've been hearing a little bit about some of that as the day went on. But today we'll really, this final session is really a forward-looking one. And we are starting off with Micah Altman, who, when I did my 10-year timeline of the Privacy Tools project, he was one of the people from IQSS that was collaborating with us right from the start. At the time, he was the director of the Murray Research Archive. And since then, he has moved to MIT, where he's the director of research at MIT Libraries and leads the program on information science there. And he'll be telling us more about robot lawyers.
Thank you very much. And as on everything else in this project, this is collaborative work. This is most immediately with Stephen Chong and Alex Wood, but this has benefited from interactions with everyone in the project, more or less, over the last several years. So the basic problem is that we were all trying to solve is how to use and share data. And one barrier to this is mathematical, how you protect privacy and share utility. Another is that legal stuff. Making sure that you've met all of the legal requirements that the institution, that the data holder, data controller are subject to. And so this project tries to bridge some anonymous social scientists' desire to use the data with analysis of all of the legal constraints. And as a social scientist, you might approach through the Dataverse, and you'll be confronted with some agreements. And those agreements are part of the sort of legal technology for managing privacy and research data, for sharing research data. And what we, there is a relationship between the legal agreements that you're presented with in a repository that governs all of the actions there, and statutory text, analysis of that, practices. But this is often bespoke, and we want to systematize this. So a primary focus of this work is around things called data use agreements. And you can think of, they're known by other names, but data use agreements are contracts that govern the transfer of data containing personal information, subject to some restriction. And they may be, include limitations on what purpose you can use that data for. You can use it for scientific research, but not for making insurance adjustments or for marketing, for example. That might be a restriction. There could be restrictions on how you have to store the data, how you have to retain it, on what you need to, who is able to access it directly, whether it's a member of your research group or a member of the public. And there are many similar agreements that govern transfer. And these agreements come out of a set of different drivers. So at the core, most of these agreements are motivated in part by some law, some legal requirements that the data subject, the data controller, the data receiver are subject to. But typically, the agreements don't necessarily just refer straight to that law and say you should just follow that. They incorporate interpretation, case law, guidance, judgments made about how to put that law into practice, standards that have developed in the community, either formally or through generalized practice, and then the local practices and motivations of the holders. And what this means is that they're very much unstandardized. So most data use agreements, standardized data use agreements are common, but they tend to be boilerplate at a very high level. So a very standard agreement that gives you some coarse-grained permission over some common sorts of data from common sources, and the rest are customized on a case-by-case basis. Usually customized for particular data transfer. They require a human to look at it. We've heard of earlier today about people negotiating for months over data use agreements and then deciding at the end of the 6 months or so that this was too much trouble and they weren't going to share the data. And so ideally, we would automate the generation of data use agreements and we would make them more modular and interoperable. And so how could we possibly go about that? Well, we need to add a computer science. And this work combines social science and computer science and law to formalize aspects of privacy legislation, to encode those in formal logic rules, use those to generate properties on the data set, and use those properties and conditions to generate licenses that reflect different laws, best practices, local practices. And to do this for all laws, for all actions is, well, it may not be impossible, like Google is not an infinite number, but it's not very practical. So in order to make this a practical problem, we have constrained it to look at limited domains and make it solvable. And our domain is the data repositories, the aspects of privacy legislation and restrictions related to storing, transferring, retaining, destroying data. And to focus on that subset of conditions that can be reasonably, that we could expect to handle automatically. Decisions about, can somebody access this through a particular click-through agreement? Does this need to be stored in encrypted form? We're not intending to handle 100% of the situations, and there may be cases in which the system says, we can't say that you can either do this or not do this. You're going to have to escalate it to human. So ambiguity is sometimes part of the law or part of our ability to interpret it, and that is built into the system, that it's possible for a human to come in the loop. And this is something that we develop iteratively. Okay, so to give you an idea of the interactions. In the first stage, we have created a logic system which takes a number of different laws. We focus first on FERPA and on the Massachusetts privacy law. We encode these laws, or the portions of them that control data transfer and storage and those actions, in a set of rules that and those rules correspond to actions over properties of the data and conditions that would satisfy your ability to perform an action. So you might say, if this data is identifiable, then if you apply differential privacy, you could release it. So that is an example of a particular condition or an act. Or you might say, if this data is, if this data comes from a particular place, is for educational purposes only, you can give it to a user if they agree to this statement, this license term, that they will use it only for this. Yes? So to formalize the privacy legislation, we use logic programming language. We aim to answer whether legislation or the particular best practice that we're formalizing either allows or denies, permits or denies. And this is a multi-stage formalization process. We've first identified the critical use cases for the repository domain. What are the action situations that we're attempting to govern? That generally involves things related to accepting data, holding it, and transforming it into something else, giving it away. Right? And from those, where do those action situations occur, and what are the key use cases? From those use cases come actors, entities, relationships, and then we have the legal side look at a domain of law, identify which documents are relevant to, say, the common rule, IRB practice, because there may be not just law, but regulations, commentary, et cetera, to summarize how and highlight how those restrictions relate to the use cases and entities we've identified in the modeling exercise. And then that can then be formalized from that human summary into a set of rules and actions. And here's an example of particular actions: deposit data, accept data, release data you can reason over depending on whom the depositor is, what the repository, what the conditions are. This allows actions to be either permitted or denied. For example, we can express that it's denied under the FERPA rule base if to release data with a particular click-through. Or we can express that it is acceptable for things that are not acceptable for release are denied under CMR. If you want to, and I think we'll skip through the next formalization. You'll see this working in a sec. This set of rules is combined with a set of questions on one side, interrogations to the user. All right. Thank you. So, thanks, Steve. So this set of formal logic is accompanied with, in the same rule base, with a set of interrogations, affirmations the user will make to establish that particular legal properties hold, and maybe survey questions that you ask them that would prompt you to make those affirmations, and then license conditions that can be used to satisfy some of the action conditions. So it may be, if something can be satisfied just through a license, then a composition, a collection of license conditions is supplied to satisfy those properties. And these may create licenses to allow a deposit, to allow the repository to retain that information, to allow users to access that information. So in summary, the input to this is a legal interview where you ask questions of the user and then you have them make affirmations of particular legal statements, such as it is de-identified under this rule. Some transaction-specific information, such as the name of the repository, the recipient, dates of study. The framework that drives this is a rules base that describes, thank you, the actions and license terms. And the output is a human-readable license. And here's an example of a template for such a license. We'll see a demo of this. So this is all working in prototype. We have, as we'll see, for a couple of different laws, sets of questions and license terms and formal logic and the ability to go from one to the other, so to generate appropriate licenses. There are a number of places to extend this. First of all, we have a number of other laws that we're interested in. Second of all, we have some interactions between between the laws that we want to be able to express. Third, we are looking at how to express reasoning over transformations like differential privacy. And fourth, this is a prototype and we would like it to go to a toolkit. So additional rule sets. This is the easiest extension. We have already encoded HIPAA and common rule on paper and are coding them into actionable rules. We've looked at the GDPR and have coded a small bit of this around usage classes, which I'll talk about. Here's an example of a rule from HIPAA. And we're also looking at how to encode data tag controls and local practices. And as you talked about, these are all composable. Right? The set of extra security controls that you use for best practice, either from data tags or your local controls, are things that you add on top of what the law requires. So you can reason about the set of all these requirements. The second extension is around particularly enabling differential privacy, but it's a technique that could be used to enable other sorts of transformations. And the idea is to reason over derived data, to have an action that allows you to say something is derived from another data set via an operator. You know the properties of that operator, and you can reason that the derived data has sufficient properties to release it to someone or to act on it further. In a bridging paper we've written, that others in the project have written, there are attempts to look at what the particular levels of epsilon, what parameters are for baseline or for different laws. And so in your best practices, you might start with a very small epsilon, and for particular legal regimes, argue that a larger epsilon satisfies the requirement of those laws. This looks very different on my screen than on this one, but that's been the case for, I'm now realizing this is not in Google Docs or something like that. But the final extension is around interoperability. And now what we have is a set of layered rule sets. So repositories and organizations are subject to different collections of laws, multiple laws and regulation systems. They also have their local practice. And currently, those are layered together so that if any of the systems deny transfer or other action of the data, it's denied. If at least one permits it, you're allowed to do it. And otherwise, you can set a lenient policy or a non-lenient policy depending on local rules. Our future interoperability goals are to make these truly portable so that third parties can use the data without seeking case-by-case authorization from rights holders. You could pass this license to someone else and have them use it under the same conditions, without going to a different set of right holders and re-asking. Then you could reason over how transformations or multiple combinations of multiple data, what the license for that should be. And that you don't have to repeat the same concept over and over in a license. And so we have a number of, well, I guess there's a calendar. All right. That was my alarm. So there are two approaches that we're working on. One is a set of conditions on common conditions on derived data. Three things. Common conditions on derived data, which are things like transformations. If you have a differentially private transformation or a k-anonymous transformation, you've removed elements of a data that allows you to make statements about the transformed work. Got it. The second is that you can state relationships among conditions. For example, if you assert that you have FISMA level access, low access controls, you could infer that you have access controls, not that meet other laws. That doesn't mean that these meet all of the requirements, but you can infer that they meet some of them. And being able to iteratively add these relationships allows us to build up license bases that are more and more interoperable. And finally, in some cases, there are taxonomies. And we have, I've had a master's student looking at the GDPR and other laws and looking at the Eurovoc and some other large taxonomies. And so this relates large families of uses in a very structured way. And since under things like the GDPR, everything has to be used for the purpose that it was acquired for, under having some much larger standard taxonomy of uses could be helpful in bringing those agreements together and in constructing consent forms and constructing data use forms and letting people know what you're going to do with the data as well as analyzing it. So there's some related work, both by us and others. And now we'll see what this looks like. This is the end and then the beginning of Steve's. What?
Just, we're gonna thank you.
Oh.
Do you want to take questions now, or? Oh, thank you. Yes.
Well, let's do the demo.
Or first do the demo before questions?
Let's do the demo.
Okay.
It always helps to
Right. So this is still the end of Micah's talk, although I'm giving the talk after this on the program. So this is just to show you a bit of the formalization of the FERPA legislation that Micah referred to. This is a formalization in Prologue. The details aren't so important. This is describing, for example, down here we have the conditions under which our formalization of FERPA would allow a repository to be permitted to have a data set deposited there. So for example, describing the fact that FERPA permits it if FERPA regards the data set DS as being in scope, if that data set DS contains information that's identifiable as defined by FERPA, and for example, there's been appropriate consent from the subjects, and the conditions on the deposit license are appropriate. And so this is a sliver of the formalization that we have. For example, there's also things on what constitutes an acceptable license for deposit, and so on. So we took this formalization, and this informed our creation of a prototype tool to automatically generate licenses. At the moment, this formalization is not directly executing when we run the tool. And what I have here is a very quick demonstration of a prototype tool. It's implemented in Java. This is at the point where somebody would be requesting the release of a data set from a repository. They may need to describe some information about why they're getting the data. We may need some information about properties of the data set. We're capturing this here with a wizard-like interview. Although, of course, the intent would be to use something that's much more integrated with, for example, Dataverse, reusing, for example, tools that were developed for the data intake questionnaire that was developed for the data tags project. So for efficiency, I've actually pre-filled in some of these questions. Hopefully that's readable. It's asking properties about, for example, does the data contain information that's going to be covered by Massachusetts privacy legislation? Yes, it does. We describe information about who's receiving the data, what they're using it for. This prototype tool has the formalizations for the Massachusetts privacy legislation and for FERPA. So here we have a question that's relevant for figuring out if FERPA applies. Does the data contain information from educational records? Yes, it does. We provide more information. Yes, it contains information that's personally identifiable as defined by FERPA. We go through the questionnaire. Eventually, we have provided all the facts about the data set and the reasons we're getting it. We're now ready to generate the data use agreement. We need some additional information for this agreement. For example, the names of the parties, the effective dates of these things. And of course, what information we need here may be determined by what terms are exactly are needed in the license. And those terms have been determined by the answers to the questions that we just provided. So having filled in this information, we now use a license template, as Michael referred to, figure out which appropriate terms have to be part of the template, and we generate this data use agreement. So this data use agreement has the appropriate names of the parties, Harvard Dataverse, Alice, and it contains appropriate terms as required by the legislation that's relevant here, FERPA and the Massachusetts privacy legislation, and has essentially the right format and the right terms that it's in fluent legalese as approved by our privacy expert lawyers. And of course, you note that we didn't have an Alex Wood sitting here behind the keyboard typing away. We were able to generate this license agreement without the direct intervention of human lawyer experts, and thus we're able to produce compliant data use agreements that facilitate the release, the use, the reuse of data. Cynthia.
I can't read this, and even if I could, I wouldn't be able to interpret it. Is it a good usage agreement?
Is it, sorry?
Is it a good usage agreement? Does it do the right thing? I mean, would Alex
so
say this is good after the fact?
I mean, so what's interesting is a lot of the time the legislation actually puts specific requirements on what has to be in data use agreements if legislation applies. So, so the point is that we get expert lawyers, Alex, and others, who, yes, they make sure this is a good agreement. Now, of course, this is a careful development process because we're going to be generating one of, don't remember the combinatorics last time I checked, but thousands of possible data use agreements. And so we need to make sure that the way we're programmatically generating these agreements, it's still going to be a good agreement without, of course, a human lawyer examining every single one of these possible thousands. So yes, we believe this is a good agreement, but this is a prototype tool, but it's the product of the process of the formalization of the interaction between with the lawyers, the terms, and the formalization which informed the development of this.
Are you arguing that it covers the basis?
I'm sorry?
You're arguing that it covers the necessary basis?
Yes, at a fraction of the effort and price of finding a lawyer who is actually versed in privacy, which many are not and do not produce data use agreements that are compliant with the legislation.
I'd add on that, just to that Desiderata, thank you, Steve, that it's a good agreement in that it has the necessary conditions, legal conditions, and sufficient legal conditions for this, and that it is, they're encoded so that you can reason about them for other repositories, for other actions, right? So it's, rather than just starting with the agreement, you could decide on this basis that you could transform data and create another agreement. However, we would like to make better agreements in that if things are regulated by multiple laws, there, rather than stating all of the current necessary conditions, we may be able to come up with simpler conditions that satisfy both, or that are a little bit more than sufficient, but a lot simpler. And so that is the next stage.
So just one other question. So even though this is a good agreement from the point of view of legal agreement from the lawyer's point of view, from an application developer point of view, say I want actually the machine readable form that you had you have acquired by collecting those questions, right? So I can find what is common across, visually, what is common across data use agreements, how I can interoperate with other systems. And so is that the plan too? You keep that,
yes.
And what is the criteria? I mean, is there to me, it would be a lot easier to read that if I would say, here's what the conditions are, how long you need to keep the data, how long to do the, like there would be attributes instead of a whole text, right? So
yes, so,
it would be
our,
nice to see both.
Our plan is to reuse Michael Barsinai's data policy model tool, which will produce a nice, JSON file of essentially answers to the questions. That is a machine-readable record of the appropriate attributes of the data set and of actions such as releasing and so on. there would be metadata associated with both the data set and with releases of the data set that you could use for other purposes. For example, finding data sets that satisfy certain criteria, understanding machine readable data on how data has been released and used.
Great.
So,
Steve, for sake of time,
yes.
probably. So let's thank Micah.
Thank
and
you.
Steve. I believe Steve introduced himself earlier, but he's a wonderful colleague of mine in the computer science faculty here. In addition to being someone who can keep sessions on time much better than I can, and he's going to be telling us about an emerging project on computing over distributed sensitive data.
Yes, so this is one of the new directions, one of the offspring of the Privacy Tools project, computing over distributed sensitive data. So, as we all know, and as Adam pointed out magnificently in the last session, lots of data is collected about individuals by lots of different organizations. Now, the interesting thing is that a lot of different organizations are actually collecting similar data. So think about the huge number of hospitals and medical centers that all collect information about patients, medical information about patients. As we all know that there's a lot of value in that data, in the sense of if we were in fact able to share this data, combine the data, we'd be able to unlock a whole lot of societal benefit. For example, being able to obtain results that are far more statistically significant when we consider a population of patients as opposed to each hospital considering their patients in isolation. But as we're all very much aware, this data contains sensitive personal information, and there are very legitimate reasons to be concerned or to restrict the sharing of the data among these organizations. So the goal of this project is to design protocols that allow us to share the computation, not necessarily the data, between these entities. So I will make this a bit more concrete, give you an example, an idea of the directions that we're heading in. But first, a bit of metadata. This project is very gratefully funded by the National Science Foundation. It's a 4-year project, and we're about 1.5 years into it. The PIs for this are from a number of institutions: Harvard, Buffalo, Georgetown, University of Alberta. And of course, more than the PIs, we have a really great group of graduate students and postdocs and collaborators working on this project. We have 3 key themes for this project: the foundations of privacy in distributed settings, statistical methods, and the third theme, programming languages and verification. And of course, within this project, most of the work and much of the excitement is really at the intersection of these areas. So for example, even though we're considering the foundations of distributed differential privacy, we're also concerned with, for example, stability and generalization. So how statistical methods interact with techniques for privacy along the lines of what John was talking to us about this afternoon about preventing false discovery. We're looking at, for example, the use of formal methods in programming languages and verification to reason about the implementation of statistical analyses written in the R language. To give you a little bit more of an idea of these specific research areas that we're working on, distributed differential privacy. So thinking about how we can apply differentially private computations to distributed data. And of course, the local model is perhaps one extreme example of this, where each individual has their own data and you can think about them as being distributed. Contrast that with a centralized approach where one curator holds all of the data and does a centralized computation. But of course, there's a range in between. Where perhaps many hospitals, each of which own hundreds or thousands of records. Distributed learning and statistical inference, again, considering how to perform computations over distributed sensitive data and understand the utility of the results of the algorithms in addition to the privacy guarantees. And as we develop these differentially private computations and implement them and want to run them, can we get assurance that they are in fact correct? That is, we are developing automated and semi-automated techniques to ensure that the programs we're writing in fact give us the privacy guarantees we think they give us. Semi-automatic because we would like to make these techniques available to non-specialists, people who are writing to the data analysts, not just the verification experts. Verified estimation and balance is a very interesting area. You can think about these hospitals each as having their individual data sets of patients. And if we wanted to do a statistical analysis, each hospital individually would look at their data set, have to throw out outliers, ones that are not appropriately statistically balanced within their data set in order to produce results that are not inappropriately biased. However, if we had a larger population, or a larger sample rather, the collection of all of the hospital's data, we would be able to keep more of the data points. That is, more of the patients would be balanced by patients that are similar, differing in all aspects except maybe the treatment. And thus we'd be able to keep them in the data set. And being able to both reason about balance in a distributed setting and also to verify that we're doing this correctly, we see as a way of helping to unlock the value in data. Stability and generalization, John has talked about this afternoon and is collaborating with others in this project who are pursuing similar goals. And then, of course, we're all interested in, if you will, the intersection of all these things, where we get to take these techniques that we're developing and validate them through implementation of prototype tools and experimentation to make sure these techniques are as useful and usable as we can make them. So let me make this a little more concrete for you all, and let's consider the setting that I've been alluding to of a number of hospitals, each with patient data, and we have a researcher who would like to analyze data, but for various reasons the hospital cannot send data directly to the researcher. Now, other presentations today have talked about other ways around this problem. For example, the ShareDB that Sam talked about, where you could perhaps have the hospitals put data centrally, or the, as Mayank talked about, secure multi-party computation, where we use cryptographic techniques for the hospitals to jointly compute on data. And these are definitely options within the space. Our focus on this project are not at those ends, but looking at other potential approaches. So, one thing that could, of course, be done is that the hospitals individually run some computation on their data sets and send the results to the researcher, who combines them in some way so as to get the value of the combination of the data. So one of the interesting and valuable questions to consider here is what computations should these hospitals be running? So for example, differentially private computations. How can we do distributed learning and statistical inference in this setting? So one thing that a hospital might be concerned about is, can they trust the computation? So presumably the researcher actually provides a computation to the hospital. How does the hospital know that that computation is doing what the researcher vouches it will do, not revealing too much about any individual? So this is where verification can play a role. You can imagine the researcher providing not just a program, but if you will, a certificate that the program in fact achieves certain properties, such as differential privacy or others. Then that computation can be sent out to the hospitals for the hospitals to run locally and send the results back. So this in some ways protects the hospital from the computation provided by the researcher. We can actually consider the reverse of that, where we can use some secure execution environment techniques, for example, Intel's SGX, so that the computation at the hospital is performed and the researcher gets guarantees that the hospital performed the computation as written, as they provided, which gives some powerful protection in both directions for both the researcher and the hospital. Now, those of you who are, unlike myself, actually involved in social science research, actually dealing with data, may just ask, well, you know, we've been doing computation or analysis over combined data sets for years in the form of meta-analyses. So one question is, why not simply use a meta-analysis, combining the results of many small studies? And as I mentioned earlier, the idea is that we can actually do better than a whole lot of small individual studies if, for example, collectively we're able to get appropriate balance in the data points and the participants of the study. And so, for example, you could imagine a protocol where the hospitals could communicate amongst themselves to try and do some form of matching within their patient populations. For example, one hospital essentially saying, I have a patient with these characteristics who received the treatment. Do you have a patient with similar characteristics who did not receive the treatment? So we can combine both of them in the data set, balance them out, and get more robust results. And of course, you would want to be able to do this without revealing too much information about individuals. And that is one of the directions that we're pushing in. We have a whole lot of exciting research going on, and in the interest of time, I'm actually not going to tell you much about them, despite the fact I have half a dozen slides. But I will tease you with them here in the hope that this will spark some conversations in the reception afterwards. So some recent work from Kobe and Uri and others is about learning heavy hitters in a differentially private way. Kobe's also been looking at remote secure storage, so thinking about essentially databases that are stored remotely, accessing them and using them, and what we can guarantee in terms of the privacy of the contents of the database. James has been examining balance, as we talked about, how to balance data sets, how to even appropriately measure balance within a data set, and understand how that affects the statistical results. Marco has been looking at the verification of differentially private programs. So this is towards the idea of getting guarantees that the computation you're running actually is differentially private and provides other privacy and security guarantees to whoever is running the computation and to the members, to the individuals in the data set. Marco and I are together continuing to work on formalizing a subset of the R programming language to enable these verification techniques to work on the actual code the data analysts are writing in the R programming language. And I, with my group, am also working on exploring the secure execution environments to perhaps give this double-sided guarantees for both the researcher and the hospital on the execution of the program, and making sure that we can actually use this low-level hardware mechanism to provide these high-level application privacy guarantees. Okay, thank you very much for your time.
I'll give you.
So I don't.
Those multiple hospitals in multiple jurisdictions and thus have different standards. You have a way of accounting for that if the legal requirements are different.
That's a great question. We have not been considering the different, at the moment, the different jurisdictions and the legal issues involved with this. So this would be a great thing for us to continue this interdisciplinary collaboration. At the moment, the way I see this is we're figuring out what is technically possible. And then, as part of that, we'll be figuring out how does this fit in a broader societal usefulness. And of course, the law also informs what is even technically feasible for us to investigate. So these will be interesting conversations for us to have.
Yeah. This is not going to fit.
Okay. Yes. Yes, there's a...
Are you doing SMC first, then differential privacy, or it's just every hospital is doing differential privacy and then we could integrate them?
We would be... We're interested in making sure that the doing computations that are, for example, each hospital runs a differentially private computation so that each hospital gets the guarantee that the data that they are releasing from within the walls appropriately protects the privacy. And for other settings which aren't necessarily using, we also want that guarantee that the hospital understands the impact of the computations, the release of data. So in a setting where maybe we're using Intel enclaves, those SGX enclaves, we could maybe get away with a computation that is not necessarily locally differentially private to each hospital, but there are guarantees about how that data is going to be combined, because the code that's run inside the enclave can be checked, verified, that it'll communicate with other enclaves only if those enclaves are running the same code. It will be combined in appropriate ways and differentially private mechanisms used on the combined data. So we're looking at a variety of things, both in the kind of local curator model, but also in forms of secure multi-party computation, perhaps enabled by enclaves. Thanks.
And it's very fitting that our final speaker for the day is Kobi Nissim. I'd have to say probably the most fortunate thing to happen to the Privacy Tools project was that Kobi had a sabbatical right as the project was starting and came here to Harvard as a visiting scholar that year, and then stayed with us as a senior research fellow through the duration or the bulk of the project. He's now a professor at Georgetown University, and during that time took leadership of many of our efforts and offshoot efforts, one of which he'll be talking about now.
Thanks, Ali, for the very generous introduction. So thanks for staying for the last presentation of today, and I'll try not to spill too much into the reception. I'll talk about a new project, relatively new project, one of the offshoots of the Privacy Tools project, which is a collaboration academically within Georgetown, Harvard, and Boston University, and also cooperation with the US Census. Okay, the main goal of this project, as we had it when we wrote the proposal, was to address two important gaps. One is there is this gap between the formal privacy models and the heuristics and techniques that are actually in use by the existing and actually also hardwired into some of the regulations and policies. And the second gap was between the rich theoretical developments in formal privacy models, in particular differential privacy, and the actual use of this analysis and publication techniques. So this is a project that combines statistics, law, and computer science. These are the PIs coming from, as I said, 3 universities, and both from the legal point of view and from computer science. It's a cooperation with the US Census that we're very proud of. And many people have helped, and probably, I hope, will continue to help us with this project, in particular, participants of the working group that was mentioned several times today, the Bridging Privacy Definitions working group that is held here at Harvard. Let me tell you how the project was conceived. I think, following the timeline that Salil had earlier today, this is going to be much shorter. We had some work done in the Privacy Tools project. In particular, we had these new collaborations that were mentioned several times today around the question of bridging privacy definitions, the legal definitions, the technical definitions. And we had a couple of products. The first one is this bridging paper that was mentioned several times. Second one is the primer on differential privacy. And that was a great starting point for thinking about a project like that. We really enjoyed working together, so we came up with a grant proposal, but unfortunately it wasn't very successful. The title was Legal Technological Tools for a Robust Regulatory Framework for Privacy. And we wanted to develop tools for regulators and policymakers to think about privacy and hopefully to incorporate ideas like the differential privacy into the existing frameworks. We got this review from the panel saying the panelists recommend that the PIs more carefully examine the literature on differential privacy, on limitations of differential privacy, in particular they suggested that we'll examine these two papers, which unfortunately are really bogus papers on differential privacy. They've been critiqued in at least these two blog posts. One is titled Exercise in Careful Misreading, second on differential privacy for dummies, echoing some of the ideas in some of these in these papers. This was really unfortunate. So we gave up. No, actually, we didn't. And we continued working in this direction. And the turning point was this meeting in MIT that Michael Altman invited us to present. Alex Wood and myself presented. There was a census team in the meeting, and we talked about the bridging work, which was then, I think, like in first steps. And there was a lot of interest and discussion in the discussion following this that we felt that, oh, we're doing something that may be important for the census. Maybe they would like to see something like that. Later on, there was a solicitation of the census administrative data and data linkages research program. We found out about it about 10 days, I think, before the deadline. We managed to put together a team and a proposal submitted in August. And then in January this year, the project actually began. So we're about to celebrate the first year for the project. So this is where we're at now. Let me give you some background for this project. So the Census Bureau, John, you were right. The census and the census use case was in our minds since the first days of talking about privacy. I remember visiting Sinja probably in 2002 or 1. And this was certainly at the center of the discussion. And this was reflected in a lot of the works that we did since then. So the census collects and analyzes a lot of data about the entire population of the US, and its publications serve as the basis for research, decision-making by policymakers, researchers, and businesses. And much of the data pertains to individuals, households, and establishments. And interestingly, the census works under this dual statutory mandate. On one hand, you have to publish data that are suitable for their intended users. And on the other hand, they have to protect the confidentiality of individuals and businesses. There are several legal standards that mandate this work by the census. The most important one is Title 13 of the US Code. But there are also other laws, like people have mentioned the Privacy Act of 1974, CIPSI is another law. And these laws protect personal information in government records. They allow the release of non-identifiable information to support scientific research and public policy decisions. Another part of the background is this evolving data privacy landscape. Since the late 90s, computer scientists and lawmakers and legal scholars have noted that the traditional techniques for ensuring privacy, what is under the literature of statistical disclosure limitation, and these techniques often fail to address privacy risks in data sharing. And there are some reasons. First, these techniques often rely on concepts that reflect the thinking of a completely different world from where we are today. The information regime was different. Access to computation, access to data was completely different when these ideas emerged. These traditional approaches are often heuristic. They only address a limited set of privacy vulnerabilities. And it's difficult to understand how different data publications combine and what is the total effect of this combination. On the legal side, there's a patchwork of existing legal, ethical, and procedural requirements for data releases in different contexts, organizations, and jurisdictions. And actually, the more we look into it, the more complex we see the picture is. On the computer science side, a new approach emerged, rooted in theoretical computer science. We wanted to understand privacy formally, differential privacy is the prominent model that has been researched. And John asked me to put the citation for the 2017 fuller version of the paper because it has a lot of extra material and extra insights there. Okay, so that was the background. And let's get back to our goal, which is to help the census use such models like differential privacy. And why are we interested in that? Technically, the census collects a lot of data and releases a lot of data. And it's a real concern how successful are the current disclosure limitation techniques and whether they're sufficient for the future. Legally, census is bound by a law that is considered to be one of the strictest privacy laws in the US. It protects a broad range of information about respondents, and it's probably broader than any other privacy standard appearing in the US. In particular, there are two sections of Title 13 that are relevant to privacy, and interestingly, Section 9 of Title 13 can be interpreted as not permitting any risk of identification. So it could be interpreted very strongly as not allowing any leakage about respondents. And this suggests that, and one has to harmonize this with the fact that the census actually has to publish information, so there is always some kind of risk to privacy. And interestingly, Title 13 is a criminal statute, and other laws that we have examined, like HIPAA and FERPA, either state a fine or other measures, but they're not, you will not go to jail. Okay? And another point that makes this project interesting is that we get to collaborate with the US Census. This is something that we were looking forward to for a long time. The Census has extensive technical legal expertise that we want to communicate with, to interact with. And the Census is going to deploy differential privacy in the 2020 Census. John has spoke about that earlier, and we want to support, definitely want to support this initiative. And interestingly, in the context of the census and because of the legal requirements, it is key that we make sure that the use of differential privacy satisfies the legal requirements. And furthermore, differential privacy is not an easy concept to understand, and explaining this concept to decision makers and the public is also important for the success of this initiative. And we hope to be involved in both. So these are the main components of the project. You can see that I'm using the same graphics as Steve, but it's a bit simpler, the Venn diagram. We have two main components. One is a technical component where we focus on statistical analysis. The second is a legal component where we analyze the statutory requirements. Let me focus on a few points. The private statistical analysis, here we focus on understanding the limits of what can be achieved in terms of privacy utility, this trade-off, in the context of statistical inferences. The legal analysis brings formal privacy models to practice, so helps bring informal privacy models to practice by tailoring them to the regulations and understanding how they meet the requirements of the existing regulations. And we also hope to have a lot of interaction between these two components of the project. One potential outcome of this interaction is that maybe there is going to be feedback from the right to the left, and we'll ask, in cases where differential privacy is insufficient for the existing laws, how should we either modify it or search for different definitions in order to satisfy the legal requirements? And also, there is the question of tuning the privacy parameters. You have heard about that several times today. There's the question of setting epsilon. And part of the work we're interested in is understanding how to make such a technical, legal, policy argument in support of setting epsilon the right way. Here are a few expected outcomes from the protocol, from the project. First, we work on bridging definitions, and we work on developing the understanding of how mathematical and legal notions of privacy interact in the context of the census work. We expect to get theoretical results in the area of statistical analysis satisfying requirements like differential privacy. We expect to evaluate some of our algorithms and to do a lot of knowledge transfer and education and in this interaction with the census team. Some current research focuses, we work on differentially private statistics and focus on non-asymptotic inference. We have some work on near-optimal confidence intervals for mean and normal population. In the break, you could ask Salil about this. Work on bootstrapping, and you can ask James about this in the break, and possibilities and limitations of private hypothesis tests, and you cannot ask Adam about this in the break. Okay. Also, we are updating our non-technical primer on differential privacy, again, a document that was mentioned several times. Let me skip that. And just to give you a flavor of some of the work, I'll finish with some highlights from the analysis of Title 13. As I said, our starting point was the previous analysis of FERPA, where we came with a rigorous argument that the use of differential privacy satisfies the requirement of this legal standard. And an approach we thought would be useful is maybe to modify the argument we had for FERPA to be used with Title 13. But, and you could ask whether the same approach works. And it seems that it doesn't directly approach, and we need to develop a new strategy because there are significant differences between Title 13 and FERPA. Okay? For instance, one is with criminal penalties, the other has civil penalties. And more importantly, the description in Title 13 is very lean. So it's, in FERPA, we had a rich text that we could base on and build a mathematical model, and we don't have something equivalent in Title 13. Instead, the standard differs to the Disclosure Review Board at the census. Okay, so here are some things that we're doing. Let me skip here. We are looking at a collection of concepts appearing in privacy law, including PII, the identification, linkage, inference, identification risk, and some other concepts. And we're trying to place them in relationship with differential privacy. We're also looking at notions of specificity in data. This is something that came up as part of looking at these concepts, relationships with the framework of contextual integrity by Helen Nissenbaum, and more recently, questions relating to differential privacy and equal protection of the law. Okay, let me summarize. This is a new collaboration between academia and the US Census, expertise from law, computer science, and statistics. And the main components are theoretical algorithmic developments, focusing on private statistics, from analysis of privacy protection required by the legal regime, and bringing the approach to privacy under the law and current practice in line with formal technical understanding of privacy. Okay, and I'll conclude here. Thank you. And if you will allow me one more minute, on a more personal plane. So I've spent 5 years in this project, and I think one person I really want to thank is Salil. I think he has been this lighthouse of integrity and inventiveness, and both scientifically and in a personal way. And I think this is something that all the team shares towards him. So thank you so much.
All right, so I'd like to do just a few more thanks as well. First, thank not only all the speakers today in this session, but also all of you and all of the people that have been involved with the project over the years, the students, postdocs, interns, collaborators, visitors. This has really been, the interactions with this collection of people has really been the highlight of the project, I think, for many of us. And those not just formally involved with the project, but those like you all who have come to our meetings and taught us all that, or some of what you know. It's really been wonderful. So thank you all. And then we should have a very special thanks to Kimia Mavon, our project manager, and Gabriella Fee, project coordinator, without whom any of these interactions that we've been talking about and raving about all day just simply would not have happened. They're the ones who've been keeping us moving through all of these years. So thank you. All right, so now we have a poster session and reception outside. One other thing I would just like to remind you all in terms of our goals for the day, we are this is not just the end of one project, but it's also, we are looking forward to the future and new interactions. We saw already in the presentation some opportunities for collaboration that we'll be following up on. But if any of you see potential interaction, please let us know. In particular, talk to Kimia or Gabriella and give them your information so that we can be in touch. And especially, as Mercedes talked about, privacy tools, some of the tools are going to be started to integrate it into Dataverse in the first quarter of 2018. And so we're really ready to start helping people share their sensitive data using our tools. And so if you have such data sets or know people who do, we would like to start working with you soon. So thank you and enjoy the reception.